We're now. Okay. Good afternoon. It is actually 12 noon, so I can say good afternoon. And welcome to everybody. Welcome to the folks who are joining us online. I am Bill Zahner, the Director of the Center for Research in Math and Science Education, along with Donna Ross, the amazing Assistant Director. We are really excited to welcome you all here to the CRMSE Colloquium and to our speaker today, Dr. Gena Sbeglia. Dr. Sbeglia is a new science educator, STEM education researcher in the Department of Biology at San Diego State University. We are so excited to have you here. We are expanding our STEM education portfolio across the college, which is really exciting. And we are really excited to continue to build the STEM education infrastructure at San Diego State. I asked Dr. Sbeglia, her talk today is going to be integrating measurement, cognition, and curriculum design to enable meaningful and equitable biological learning. I asked Dr. Sbeglia for one interesting fact about herself that we could share. She said, first, there is nothing interesting to share. That makes me nervous whenever someone asks me. Then she shared that she lived in Madagascar studying green-tailed lemurs for a year, which is very interesting. So goes to show that persistence in questioning. We are just so excited to have you here. And Mike, there's a technical question.
Yeah, does anybody know what multi-tin means? I'm just getting a request from Sam.
Yes.
Does that mean you need to turn off your audio?
No, that means you have to.
People pin.
That's what it interpret.
Oh, yes, that's right. I was wondering that.
And then you have to pin one.
You should be able to. That's actually,
There you go.
Okay, and if anyone is on the Zoom call in the room, please do not join audio. That wreaks havoc on the call. So with that, I'll hand it on. Thank you, Dr. Sbeglia. Are we good to go, Mike?
yes.
Okay, wonderful. Take it away.
Thank you so much. It is a true honor to be presenting here to CRMSE people. This is the first talk I've given in person in like 2.5 years. It's very exciting, and I couldn't actually think of a better group of people to have that first talk be too. I'm very much looking forward to feedback. Some of what I'm going to talk about today is some of my older stuff. It was in my job that now was quite a while ago, but some of it's newer things that are starting to try to bring a lot of the pieces that I'll be talking about today, bringing those pieces together, and then applying those pieces to introductory biology at SDSU. And so some of this is slotted to actually happen next semester at SDSU in the introductory biology program. So I'm very, very much looking forward to hearing your feedback. So I'll tell you, I guess, a little bit about myself. I love learning about Miranda. I didn't make any fancy slides with math and stuff. I should have, but so I did my my Bachelor's of Science in New York, and then I went to St. Louis to do my master's in biology, and then back to New York at Stony Brook University, where I did my PhD in biology. And I was actually studying ring-tailed lemur social behavior and disease transmission. There's a lot of genetics, a lot of lab work, a lot of growing, collecting poop, and getting bacteria and sequencing stuff. And that was all wonderful. But I was exceptionally fortunate during that time to meet my first biology education researcher. And it's fair to say that that person like totally changed my perspective on teaching, learning, and research, frankly. I had always thought education seemed like it could be research, like it felt like research. And I remember I first tried to delve into the literature, and I clearly didn't know where to look because I was really put off by the biology education literature I was reading. And at the time, I didn't appreciate that biology education as a research discipline is a new discipline, right? Education research, of course, is old and has brought amazing evidence-based ideas forward that these discipline-based education programs are using and applying to biology, but I was discouraged. And so I was fortunate to meet Ross Name, who during my PhD, and then I embarked on a 5-year postdoc with him after I graduated with my PhD, also at Stony Brook. So I was at Stony Brook for a really long time. And that was extremely formative for me because I was able to witness over the course of, I think, 9 or 10 years, the reform of a 570-person gateway biology course that was taught in a large lecture hall with absolutely no evidence-based anything happening at a very diverse institution, public institution. I was able to be part of and observe that reform all the way through to what is now a completely flipped active learning course. And that really informs a lot of my research and it informs a lot of how I bring that research into practice. So I guess enough about me. Let's talk some specifics here. I got to probably click on it. Okay. So state of STEM. Now I'm preaching to the choir here, but students identifying as members of historically excluded groups or HECs now come to approximately 70% of college students enrolled in STEM classes and they enroll in STEM classes at similar rates as white males. But fewer than 40% of students who enter college intending to major in STEM fields complete a STEM degree. This is across the board. So there's a lot of students who are effectively weeded out of the system. And what has been identified is that HECs comprise only 45% of undergraduate STEM degree recipients and less than 25% of the STEM workforce, even though they make up 70% of undergraduate students who are interested in STEM. So what we're seeing here is the gateway STEM courses diverse as the US population, but the diversity is not maintained and at quite an alarming degree through graduation. So under preparation is the most frequently significant predictor of student outcomes in research studies that focus on this question. Many talented students are interested in biology. They enroll in introductory biology courses. They declare biology majors. But traditional lecture-based courses inadvertently punish students who had a low quality high school education. So, I mean, the bottom line is that undergraduate biology education needs to change if we're going to improve the quantity and the quality of learning, meet the needs of diverse learners, and inspire a future generation of scientists that are representative of the nation. And this is, in truth, the goal of, and should be the goal of faculty teaching undergraduate students biology. So addressing inequities in STEM education requires research and action. And it requires this at multiple scales. I have 3 scales highlighted here. The student scale, where we can ask questions like, are our attempts at change improving learning and addressing the psychosocial needs of our students? The classroom scale, we can ask questions like, how can we leverage our knowledge of student needs to design, implement, and assess introductory or gateway biology curricula? And then faculty scale. How can departments determine if faculty are changing in a way that supports diverse learners? And so in today's talk, I'm actually only going to talk about these 2 scales so that I can also introduce some newer work and how it applies to the biology courses at SDSU. So we'll start at the student scale. And again, this question is, how are our attempts at change, improving learning, and addressing the psychosocial, but also the cognitive, frankly, learning needs of our students? So understanding student cognitive models is essential to effective teaching and learning, but much of the work in biology education remains detached from cognitive theory. And this is a problem because the cognitive models of biological thinking frame the way we collect our data and impact the validity of the interpretations we make from those data. And so we can't really know if our students are learning biology or really anything, or if they're feeling a sense of belonging in our classrooms without aligning our measurement tools with how students actually think with their cognition. And so student reasoning has been found to differ by context and scale. It's not just biology, but this is a broad finding in many, many fields. And so, for example, in biology, students may think differently about evolution happening within a plant versus an animal versus bacteria. This is actually a well-researched question, and the results are consistent across universities, courses, and students, no matter their developmental progression in biology. Students may also differ in how they think about evolution at different scales. If we're talking about the evolution at the scale of a forest, plant, cells, or if we're talking about other ecological processes at forests, plants, and cells. Students may also reason differently at various scales of social organization. Right? Students come into the classroom embedded as their individual self within broader social organizations. So for example, how a student feels about the conflict between evolution and their religion or their religious identity may differ if they're being asked about it at the individual scale or if they're being asked about it in their community more broadly. And this is where I'm going to start today, is talking about student cognitive models and how we use those cognitive models to design measurement tools. In this case, designing measurement tools assess students' perception of conflict between that they have with evolution, and to do so at multiple scales. So measuring latent variables, as I'm sure everyone here knows, requires generating reliability and multiple forms of validity evidence for the test. It requires using something like item response theory. It doesn't have to be item response theory, but to establish quality measurement and to construct linear measures of the latent trait on a logit scale using counts of quantitatively ordered rating scale response data. I'm not going to go further into this. This is not the sexiest of stuff, but foundationally, this is really, really important to designing measures that are robust and that whose resulting data can be interpreted in a meaningful way. And I'm happy to answer more questions about this after the talk if desired. So I developed, using these principles of measurement and principles of cognitive theory, an instrument that measures students' perceptions of conflicts with evolution and at multiple scales: the individual scale, the family scale, and the community scale. So their personal perception of conflict, how they view their family's perception of conflict with evolution, and how they view their community members' perceptions of conflict with evolution. So conflict with evolution, why? Why this topic? Conflict with evolution may be linked to acceptance of evolution, evolution understanding, belonging in biology classrooms, and ultimately career choices. Right? It's unlikely that a student who feels conflicted with evolution is going to choose to go into an evolutionary biology field. It's not impossible, but it seems somewhat unlikely that that will happen. And few studies have actually empirically quantified conflict. It's talked about in the literature quite a bit, but few studies have empirically quantified it, and none have done so at multiple scales. And typically when it is talked about, it's in the context of religion only, where students can, of course, feel conflicted for many reasons beyond religion. And many religious students are not conflicted at all. In fact, a lot of times our religious institutions do a really robust evidence-based job of interacting with their students about religion and evolution and how these two concepts live in different worlds. They solve different problems and they don't need to conflict. So this instrument that I call the CRMSE could facilitate more frequent measurement of this construct in evolution settings, raise instructor awareness of conflict levels in their students. It might surprise a lot of faculty, and foster rigorous evaluations of educational interventions designed to reduce it. So any instrument measuring the perception of conflict with evolution should do a few things. It should consider the nature of human social structure. So now we're not just talking to individuals here when we ask them about their perceptions of conflict. We have 3 scales that I've got here. Pro-conflict as it relates to values, cultures, and beliefs, which can encompass religion, but can also encompass things beyond religion. And it shouldn't constrain sources of conflict to single topics such as religion. The goal here is to broaden the scope of conflict measurement beyond individual conflict and religiosity to better capture how conflict is conceptualized by students. And so this is kind of a schematic of what this instrument looks like. It is conceptualized as a multifaceted measure at 3 scales: individual, family, and community. And each scale has indicators related to values, cultures, and beliefs. And so we've implemented this instrument for now several semesters in undergraduate biology courses. And we have received feedback from both students and experts in this area. On content domain, we've administered this survey to now over 1,000 undergraduate students that were enrolled in a Gateway Biology course, and the instrument showed suitable reliability, content validity, internal structure validity, and convergence with similar measures. How, on the other end, are robust and can be interpreted in a way that is meaningful. And so this instrument's been published, and there are currently 2 projects where this instrument features. I'll talk to you a little bit about those projects now. The first one addresses causal relationships among conflict and other variables, right? We're not just interested in understanding students' conflict. All of this should scale up to student learning and success in classrooms. So what currently has been done here is that using latent variable path modeling, I modeled a causal relationship between conflict perception using this instrument that I developed, the CRMSE, and evolution acceptance. And so more specifically, the 3 scales of the CRMSE were modeled as being causally linked in this way, where family and community conflict are causally linked to individual conflict. And then evolution acceptance broken down at 3 scales, right? Linking it with how students think about evolution: microevolution, macroevolution acceptance, and human evolution acceptance were modeled as being causally related to conflict. And importantly, religiosity, background variables, and evolution knowledge are controlled in this path model. So what we see here very broadly is that conflict contributed to the explanation of evolution acceptance above and beyond the contributions of religiosity and evolution knowledge alone. And so more specifically, assuming a correct model, both family and community conflict had unique causal contributions to individual conflict, with family showing a stronger but modest impact. Furthermore, individual conflict had a significant causal impact on all scales of evolution acceptance, importantly, above and beyond the contributions of religiosity, evolution knowledge, and background variables alone. So conflict, including conflict in our models, is addressing a source of variation in evolution acceptance that religiosity, background variables, and evolution knowledge cannot address or have not addressed in this sample. So the second kind of study that uses this measure is broadly a conflict reduction intervention study. And so this is kind of where we start to work in classrooms. And so to kind of set this up, what I want to first say is that in my research, but also nationwide studies, Black and Hispanic students have tended to begin biology instruction with lower evolution knowledge and acceptance, higher religiosity, and higher levels of conflict with evolution than white students. This is actually quite a consistent pattern. And what this pattern means is hotly debated in the field, and how to frame discussing this pattern is hotly debated in the field. As you can imagine, could be problematic ways of interpreting this pattern. This is a pattern that we've identified in our sample, and this is a very large sample at this point, and many others have as well. So given this landscape, it's important to ask if our gateway courses are sufficiently removing barriers that can impede student learning. We know students are coming in with different amounts and qualities of prior preparation. We know this. Actually, this isn't new. We've known this for decades. And so are our courses removing those barriers successfully? That should be the next question we ask. And so we've begun to build interventions into our courses, the Gateway course that I was previously involved with at Stony Brook. And there are many kind of interventions that we use. I'm not going to go into detail here, but some of the examples are shown below, where we introduced videos with African-American female biologists talking about the importance of evolution in their work and in a socially relevant context. We've introduced videos from religious scientist Dr. Francis Collins discussing how religion and science intersect or do not intersect for him. And a broader module on the nature of science, where students are taught the boundaries of science. What is the domain of science? What questions can science answer? And what questions can religion answer? With keeping in mind that both are different ways of answering questions, different ways of viewing the world, and different ways of knowing. And so what are the boundaries between those two? So there's, those are some of the interventions that we used for this research-based version of the course. And so here you're seeing some early results from this study. And what we're showing here is that the traditional course in blue, I think I actually skipped these. Yeah, switch these, I mean. So there's a larger reduction in personal conflict with evolution in the intervention semester, which is the blue. So a larger reduction in conflict in the intervention semester. And disaggregating these data by ethnicity and race, we can see here that the pattern is the same, is that there's still this larger reduction in personal conflict in the intervention semester than in the traditional semester. And actually, this is a larger magnitude decline than we see for the sample overall. That was the prior slide, the sample overall. And so that's somewhat encouraging. So the first one answer to this question are our attempts to change improving learning and addressing the cognitive and psychosocial needs of our students. These results really talk to the psychosocial needs of our students. Development of the CECM, studying the interrelationships among variables, and conflict reduction interventions. But I'm also interested in how our attempts to change are improving the learning that our students are experiencing, so their cognitive needs. And so I'll start here. This is a list of misconceptions about evolution. There are many, they're common, they're had by basically everybody, and they're frequent in our undergraduate students as they enter Gateway Biology courses. And so this is recently published work that basically asks the question, is active learning, which we've all, for decades been told this is what we should be doing in our classrooms to help student learning, is that enough? Or do we have to address misconceptions head on in addition to active learning? That's basically what this study is asking. And so the design of this study is kind of represented here. Each iteration or each square is a different semester of the course. And active learning is represented by AL. So this light gray circle is active learning, the amount of active learning. And then we see misconception focused instruction in the kind of dark gray here, and then an overlap. And so each semester course had a different relative amount of active learning, a different relative amount of misconception focused instruction, and a different amount of overlap between the two. And I'm not going to go into detail about what our misconception focused instruction looked like, but if someone wants to ask questions about that, I'm happy to address it. But the main point of it is that it explicitly talks about misconceptions. It doesn't just focus on the right content, but engages with students about the misconception itself and why it's a misconception. And so this basic pattern here is that across the course iterations, you can see these sample sizes here, there's an increase in the amount of active learning and an increase in the amount of misconception focused instruction. There also happens to be an increase in the overlap between the two. And so we've collected pre and post measures of evolution understanding, and this is what we find. And so broadly here, taking a look at this whole screen, the arrow indicates the direction of increasing evidence-based practices. So higher active learning, higher misconception focused instruction. And so our first finding is that higher doses of active learning and misconception focused instruction were associated with significantly larger knowledge gains in panels A and panel D. Those are both showing knowledge, with more active learning, more misconception focused instruction being associated with higher learning, pre-post learning. But we also find that misconception focused instruction produced significant learning above and beyond active learning alone. So the more misconception focused instruction, there's an even higher impact on learning outcomes than when it's just active learning alone. And so this is published in Bioscience this past September. So I've now answered this question two ways. There's obviously many ways to answer this question, and we can move on to the classroom scale. So a question we can ask at this scale is how can we leverage knowledge of student needs to design, implement, and assess introductory biology curricula? Intro bio is where we have the most diversity that we're ever going to have in our majors at our institution. That's where they are in introductory courses, right? So this is my primary focus for understanding what's going on in the classroom is the introductory biology classrooms. So I'm going to actually shift away from evolution for a moment into another really important area of knowledge for undergraduate biology students. And that is the area of matter and energy, which is one of AAAS's major areas for content learning that undergraduates are expected to have by the time they graduate college. Materials for matter and energy are underdeveloped. And national studies indicate that 40 to 60% of undergrads have not mastered current New York State middle school matter and energy learning targets, middle school learning targets. This material is actually quite difficult. So it's not actually surprising when you start really getting into this content. But that's a problem, right? And we need to address that with the design of curricula that do something different than what they've been doing before, because they're clearly not working. So to address the gap in the availability of matter and energy resources, I worked on an OER grant, Open Educational Resource Grant, to develop matter and energy digital assets for learning for Gateway Biology courses. And so basically what this project was developing curricula that were modular, meaning that people could take some parts and not others to implement it into their courses, and digital, all of it's digital. And there's 5 areas where we developed these, this material: active learning materials. We developed a video library on matter and energy, clicker question database, web-based applications, and an assessment instrument called the MOMO, which stands for the Movement of Matter in Organisms. So this work, builds on what we know about optimal learning. Okay, so the development of all these resources builds on what we know about optimal learning. And what we know is that optimal learning builds on prior knowledge, requires the integration of knowledge structures, and builds up transferable knowledge structures. And a problem with most undergraduate curricula is that it generates ephemeral knowledge that's not connected to cognitive frameworks or to the real world. I mean, matter and energy answers the question of how we lose weight, yet frequently taught in a way that's not connected to the real world. These digital assets use a cognitive science approach called contrasting cases, in which multiple cases reflecting the phenomenon are provided. For example, the movement of matter and energy in a turtle, an animal, a fungus, and a plant. So we've implemented the materials in undergraduate biology courses and the MOMO instrument to measure at pre and post test what the matter and energy knowledge is of the student sample. And the results are shown here on the right, is that we see overall students' mean probability of answering items correctly nearly doubles from pre to post test with large effect sizes. But one thing I want to just note here that hasn't been published yet is that while all students gain, we see that students from historically excluded communities have the lowest pre-test matter and energy knowledge and tend to gain the least, right? So our work isn't done here. And so this is a continuing project. There are 3 web-based applications that we've developed, and they will be used in the introductory biology courses at SDSU. I can kind of show you, let's see, will this play here? And so students log into the app. This uses a platform called R Shiny. So you code the apps in R, and they can be implemented to students with just a simple link. Students log in, they kind of go through the whole thing. They can do it in groups, they can do it individually as homework. Yeah, so R Shiny requires a special server, a Shiny server, that is currently being implemented at SDSU. If it goes, they're having issues right now. I have to respond to an email, but that this server should exist at SDSU really soon and can be used for courses beyond this one. But there are 3 apps that will be on that server available for introductory biology students. This is just a kind of walkthrough of one of them. There's also some new videos that have been designed since that prior publication, and as well as some new activities. So this work so far was addressing this question of how do we leverage our knowledge of student needs to design the kind of new curricula. But there's also, and evidence-based assessment was the first answer to that question. But I think it's also really important that we start, when we're thinking about classroom, and we're thinking about learning, we're thinking about equitable learning, we think about equity in education, and we think about indicators of equity in particular. And so the NRC in 2019 has phenomenal policy paper, conceptualized educational inequity as the persistent pattern of between-group disparities in 7 education-related domains. They've identified 7 of them. What you see on the right is one of those 7 domains. Learning and engagement is just one of their 7 domains. It's the domain that I work in most often. And they identified specific indicators of educational equity in that domain, specific constructs, and they proposed specific measures. It's really, really, really valuable publication. And I am now proposing additional measures in some newer work of educational equity. And these newer measures that I'm proposing as indicators of educational equity are measures of educational debt. So I didn't come up with educational debt. But it's, I'll tell you who did in a minute. So, but over the past decade, demographic disparities in educational outcomes have frequently been approached by documenting so-called achievement gaps, right? We've all heard this. And we may have also heard that, that this is perhaps a problematic framework. So in this framework, achievement gaps typically refer to differences in test scores between marginalized and advantaged demographic groups. And I would say at this point in education, research within biology at least, this achievement gap framework is on the outs for lots of really important and accurate reasons. The educational debt framework has been proposed as a equity-aligned alternative. It was proposed by Landis Billings in 2006, where she eloquently described the problems with the achievement gap framework a very long time ago. It took us all a while to catch on. And it's a powerful social justice aligned approach for conceptualizing demographic disparities in educational outcomes. And so let's talk about what that framework may look like in classroom at data, at pretest and data at post. What this actually means, the educational debt kind of idea, is that students enter courses with differences in knowledge, proficiencies, and experiences due to systemic inequities. You can see that on the left, where marginalized students in blue start out at a lower point and end at a lower point than advantaged students in yellow at pretest. I'm sorry, they start out at a lower point at pretest. That's all pretest. These pre-course differences are conceptualized as the educational debts that society owes to students. Quantitatively, this baseline debt that we see circled here in red is reflected by lower pretest scores for historical students. And then what happens throughout the course of the semester indicates what happens to that debt throughout the course of the semester. And in this conceptualization here, which is by Van Dusen and Neeson, the debt can either be mitigated, where both groups, no matter where they started, come to the same point. The debt can be perpetuated, which is in the second panel here, where everybody learns, they learn more or less equivalently. And what that means is that marginalized students are still have lower knowledge than advantaged students at the end of the course. And of course, debt can be exacerbated, in which case marginalized students actually learn less than their advantaged counterparts. And I think there's a lot of evidence suggesting that this panel all the way on the right here is actually what's happening often for a lot of constructs in introductory courses. But it has not relatively new these disparities. I can't for sure, but as more people use it, I expect we'll find that. So some of my more newer work is applying a very large data set that was generated over the past 8 or so years of pre-post evolution learning and matter and energy learning, disaggregated by salient student identities, and there are many of them, and applying these data to a modified version of this framework. One limitation of this framework is that, and I'll go back to it for a moment, there's an assumption that learning happens, right? And actually, there's not a lot of studies on learning in biology education, fewer in evolution education, and a lot of them show learning doesn't really happen in a lot of cases. So the assumption that learning happens is not necessarily consistent with what we're seeing in real classrooms at the moment. And so I'll be kind of modifying this framework to fit that reality. This work builds upon theoretical and early empirical discussions of educational debt by adding a second empirical dimension, magnitude of learning, to generate more nuanced measures of educational equity in line with NRC recommendations. This work is situated within NRC's policy document. I think an important thing to point out will disagree with is that of the many education-related factors that must be modified to generate systemic institutional change, learning has received relatively minor attention, yet must be part of this multifaceted lens through which we understand the removal of barriers to success. It's important and necessary and essential and foundational that we improve students' sense of belonging, motivation, STEM identities, feelings of inclusion in our classrooms. That absolutely must happen. But we also must produce phenomenal scientists if we want to diversify our field. And so learning has to be a centerpiece of our equity-focused work as well. And it often is not, at least in some areas of biology education work. And so the work I just showed you was my answers, my current answers to this question of how we can leverage knowledge of student needs to design, implement, and assess introductory biology curricula. And this is how I did it. But of course, it's not just enough to do this work at a single scale, right? Addressing these inequities in STEM education will require that this work is done at multiple scales and that these scales actually interact with each other and have feedback with each other. So now how do we bring the pieces that I've introduced to you today together at SDSU in a truly applied way that has the potential to make change for students? So this is how I'm doing it. And it's happening next semester, so I want the feedback and I want it now. Okay, so nationwide, you all know this, introductory courses have the greatest persistence and retention problems, right? And research, especially like Freeman's 2014 paper showing how much class size appears to be at least correlated with student learning and student outcomes and equity of student learning. The lack of appropriately sized classrooms is likely limiting appropriate and equitable learning experiences for students. It's really hard to implement active learning in the ways we all want to do it in a 300, 400, 500, 900 person lecture hall. Yet institutions are still building 900 person lecture halls. But faculty can be extremely effective in rooms that are appropriate for learning. And so this is the pitch, literally the slide is part of a pitch I gave to people, many people in this university to convince them to do this, which is to let me change the current lecture hall design of Bio 204, which is a gateway organismal biology class at SDSU, from a 300 person course in a large lecture hall to a 100 person active learning course that still serves 300 students by magic. No, by repeating that course 3 times, but flipping the course that all lecturing is actually happening by video. And the only face time that students experience is active learning, and it's once a week. And so the important thing about this design, which I have to give credit to Dr. Ross Name for this basic design, no additional faculty are needed. No additional TAs are needed, unless, like my department, you've never given a TA to the most introductory, highest needs course in your department. And then you have a new faculty member come in and say, yeah, I need you to give me a TA because these students, the ratio of faculty to TA is not enough. But only one TA, one faculty member is needed for this shift. And students can be in 100 person classrooms where they meet once a week instead of meeting 3 times a week because all their lecturing is now done online. And you'll notice this 36 UTAs thing there. I'll talk a little bit more about that in a minute. So I pitched this about 1.5 years ago now. Drew a picture of the classroom in case people's imaginations limited them. Scheduling is actually one of the hardest parts about this shift. Universities have really rigid approaches to scheduling. Classes must be Monday, Wednesday, Friday, or Tuesday, Thursday. They must be 50 minutes or 120 minutes. If you want a classroom one day, you have to reserve it for all 3 days. And so meaning if it's not available on Friday, but you only want it Monday, you can't have that classroom. So really rigid scheduling kind of rules that are highly antiquated and really make it hard to shift courses to alternate formats that are better for students. And so this is what was needed, a 50-minute time window 3 times a week for active learning. And so ideally like all on Fridays. So, 12 o'clock, 1 o'clock, 2 o'clock, and 100 students attend each of those sections. And then all the material that's lecture is going to be given by a faculty member via recorded video. So this is a great kind of proposal, in my opinion, of course, but it can't actually happen without a lot more members on this instructional team. And that's where undergraduate TAs come in. And so I developed a new 3-credit undergraduate TA professional development course. And this course is a 3-credit course. It is going to be offered for the first time next semester. And it includes core lectures on and active learning sessions on cognition, effective feedback, effective and equity-centered group work, diversity, equity, and inclusion. And it includes weekly PCK or pedagogical content knowledge kind of modules on each active learning session so that these UTAs can go into the classroom, not just knowing the content, which they will know well probably before they even come into this class because they will have taken Bio 204 before. They will also know students' likely difficulties with the content, so they can actually engage in student misconceptions and reasoning and help them work through those challenging ideas. And then these UTAs as part of this course will support 3 groups throughout the whole semester in this active learning class. They will attend the active learning sessions and support those same 3 groups, which will be about 12 students the whole semester. And so it's happening. These are the times. I know where it's going to be. That's all great. The next step, of course, is recruiting the TAs. And so registration opens next week. I'm very nervous about it. And I am going to be putting together an application very soon that I will be sending out to former Bio 204 students, the ones I have information about, their contact information. But I think I only have that for 1 semester. So I might need to somehow, I don't know, find more students who've taken Bio 204 because I need 36 UTAs to agree to take part in this Bio 496 course. I'm also working on getting it to be part of the biology major as an elective. I don't know if they'll let me do that, but I'm trying. But it actually does give a grade, so it's not a pass-fail. Okay, so that's what I got, and I would love any questions. I mean, there's a lot of people who thank for this work, a lot of funding agencies, the Bio 201 students who really taught me and Dr. Rossnay taught me everything I know, and I have a lot of thanks for all of them. So I'd love to take your questions at this point.
We already got a question.
Okay. Do I stop? I should stop sharing? Okay. Okay.
Okay. And if you stand kind of right where you are, you're visible at least.
Great.
There. So from Annalise came the question, have you seen differences in resistance to certain topics in biology? Evolution can be very charged in terms of identity, but maybe photosynthesis or genetics, not so much.
Yeah, that's such a good question. There's so much there. So yes, evolution is a charged topic. And this is not just a fact of Southern institutions and Southern student samples. This is a nationwide reality, is that students struggle with thinking about evolution, and they struggle with thinking about evolution as it intersects with their identity. They do, and they did in New York. I've started collecting pretest data at SDSU in the introductory biology course. They do here, not everyone, but a large fraction of our students do struggle with thinking about evolution and accepting evolution. And what my work and many other people's work has shown is that students from historically excluded backgrounds have lower evolution acceptance than students from advantaged backgrounds. And so it clearly is an equity issue in our classroom, addressing students' discomfort with how a main topic in a biology class intersects with their identity. In fact, it turns out to be inequitable not to explicitly address that really important discomfort that students have, especially if our goal, our broader goal, is to encourage persistent participation in our field and in our careers that relate to evolution. So yes, I've noticed it. Other people notice it too. You must explicitly interact with it. One question that I am thinking a lot about is, of course, how do we do that? And there are many ways people have tried, but they're all at the individual level. They all focus on the student as an individual, but as I have talked about previously with perceptions of conflict with evolution, students don't exist as individuals. They exist as members of their broader families and their broader communities. And so when we're trying to help students feel an acceptance of evolution or a inclusion in this evolution space, do we just address the individual themselves, or do we help them think about this more broadly as it relates to their communities and their family? So that's, I think, an important question that's worth thinking about. The idea of, oh, and I should say, you can change students' evolution acceptance. Every semester that I have data for, student evolution acceptance has increased, and it has increased for students of all backgrounds, but it increases very little. It's really hard to change, really hard to change. Photosynthesis, that is worth talking about, because one might think that photosynthesis is not linked to student identities. But movement of matter and energy is very much linked to student identities, it turns out, because every student has interacted with the natural world since the day they were born. They've interacted with the movement of matter and energy since the day they were born. They felt the energy that radiates off of fire. They have gained weight from a small child to an adult. Perhaps they've lost weight. They've interacted with the movement of matter and energy, this concept in biology, since the day they were born. And their ideas on this topic, a lot of which are incorrect, not just students, but broader population as well. Right, most of the way we lose weight is carbon, we exhale CO2. That's how we lose weight. The vast majority of our weight, right? That's how we lose it. And when they hear that, we have had students get mad at us because this is knowledge that they have had for 20 years. And that is personal. And so we're dealing with that as well with these ideas. I think this is maybe a unique challenge to biology that some other fields don't have, that students have interacted with the living world their whole life. They have lots of mental models that they've built up since they were young children that have gone uninterrupted or uncorrected throughout much of their life. And then they come into an introductory course and they find out they've been wrong for 20 years. That can, I mean, it can cause stereotypes, it can cause lots of problems. And so knowing that going into designing a course is absolutely essential, both engaging with, explicitly addressing those misconceptions, and also helping students recognize your idea about that topic is logical. It makes sense why you thought that. In fact, the majority of people, including doctors, think we lose weight by sweating. So yes, thank you for that question. Yeah.
Could you talk more about the misconception-focused instruction and how that is distinct from active learning?
Yeah. So oftentimes it does interact. But what misconception-focused instruction is broadly is where the misconceptions about evolution are central to the design of whatever the lecture is or whatever the activity is. And so to give you an example of an activity that we use that was considered misconception-focused instruction, we would give students an explanation, like a student explanation of evolution, and ask them to identify the misconceptions in that statement. So that's one example where students are actively thinking about, okay, well, what are the misconceptions here and why are those misconceptions? And how would I correct this statement? That's kind of one example of how it's done. Now that is an example of active learning as well. The examples that we have of misconception-focused instruction that's not also active learning, and you can argue with me that it is, I think that would be reasonable actually, is a video that just identifies, here's 10 misconceptions, this is why they're misconceptions, this is the correct way to think about it. Could be active learning, right? Because students could be engaging actively, but the field does not have measurement tools if the field does not have good measurement tools to identify and measure the amount of active learning in the classroom, there are some tools that exist, they do not, as far as I know, work necessarily on videos, right? So there's some issues with the measurement of the amount of active learning, but that was coded as not active learning because the instrument we used considered that not active learning. But one might critique that. Yeah.
I have a friendly provocative question.
Okay.
Because I keep hearing the word misconceptions a lot.
Yeah.
I went to grad school at Berkeley, and as you know, there are some deep divisions, some in the field around even using the term misconceptions as a preconception, an alternative conception. I'm thinking particularly from a knowledge and pieces standpoint or something like that. And so I'd just like to hear you speak a little bit more about possible maybe advantages or disadvantages of how that frames students and how you're thinking about that in the work.
Sure. Yeah, so I mean, I think there's two pieces to that answer. The first is that it's true, the word misconceptions. The word itself has been, maybe 10 years ago, I don't know, has been identified as perhaps problematic, and there were some really high profile papers on that it's really problematic, it's student deficit thinking. There's some papers on that. That kind of hate of the word misconceptions has not really persisted. It's now more or less accepted again, though some people will never be okay with it. So the use of the word misconception was carefully considered, and we did choose to stick with the word misconception over alternate conceptions because at this point, the state of opinion on that word in the literature is okay. We didn't know if we would receive pushback when we published it in Bioscience. We did not. We had a very prominent education researcher review the paper. But I think your bigger point isn't just about words. It's probably, and correct me if I'm wrong, about thinking about, are we thinking about what students are lacking? Are we taking a student deficit approach in the first place by focusing on misconceptions? And I think that's an important point to always be aware of and always ask ourselves, is this approach taking the perspective that there's something wrong with the student? So if that's the perspective your approach is taking, then you're in big trouble. Your students are in even bigger trouble. And so I would argue that certainly a misconception perspective can be that. It can be situated within a deficit framework. But frameworks matter. And frameworks dictate how we ask questions, how we interpret patterns, how we collect data, how we make changes to our classroom based on those data. And so if a misconception-based approach is framed within, let's say, an educational debt approach, or there's nothing wrong with the student, there's something wrong with the environment, an environment deficit approach, then we have the freedom to understand how students think, right? Because that's the truth is that these misconceptions exist. So we have the freedom to both understand how they think, believe that they think that way, and that there's darn good reason for them to think that way, and make changes to our curriculum based on our knowledge about their thinking, which really is what needs to happen. So something that I think the field needs to be careful about is saying that the particular action or approach itself is problematic when it might be the framing of that approach that's problematic. And I think that that's kind of what maybe is happening in the misconception field, is that if you're having a deficit student thinking model and you're teaching misconceptions to students explicitly, without a doubt, the way that that's going to be done in that classroom is probably going to be problematic, because it's unlikely you're telling students there's nothing wrong with having that misconception. In fact, that misconception is so reasonable and logical that the vast majority of people have it. You can even show them videos of Harvard students who go on and on about all the biochemistry courses they take, and then saying that where the mass and the log they're holding came from is the soil. Harvard students, right? They're the best, aren't they? And of course, the mass in that log came from the air. That's where it all came from. Well, all the carbon. That's where all the carbon stuff comes from the soil. But the vast majority of that comes from the air. And so, taking it from an environment deficit framework, you address misconceptions in a very different way. So I think that is a great opportunity to say frameworks really matter in everything we do, which is also why I haven't really published much on educational disparities yet. I've seen the results in my data for like a million years. But the frameworks are really underdeveloped in about disparities in student progress and learning. And so I think this educational debt framework might be a valuable step forward.
I'm going to ask a question on behalf of the chat. This is coming in from Annalise, who asked a question saying, if only 25% of STEM graduates go into the workforce in, I think, in STEM, is there a way of measuring the impact of STEM education in the lives or the communities of graduates who do not go into the STEM workforce?
Yeah. We better figure out a way to do that, right? I mean, I don't think I have the answer to that. But there's a lot going on there that the field and certainly all individual researchers do not understand. And, you know, some of my more recent work that's really quite nascent has actually involved interviewing students who've taken Bio 204, 201, sorry, that's Bio 201, it's a course from Stony Brook, have taken my course, interviewing these students about their experience in the course as it relates to evolution, as it relates to conflict, as it relates to their communities, and their family, and their social structures, really trying to get at how the course interacted with really salient parts of their identity. And the focus of those interviews, actually, a lot of it was on their communities they come from, their family, and their broader communities. And so these interviews were done with Black and African American students. And the idea, and very rarely do we actually talk to the students that are the most negatively impacted by our gateway courses. And so that was the goal of these interviews. And I was not giving these interviews, don't worry. I have a really, really skilled, he's graduated from his undergrad, so I can call him an education researcher now, student who is Black African American himself and interviewed these students. And so similar work I would like to do with more communities of students at SDSU to try to understand kind of what their thinking really is on careers, what their family members is on career choices. And so that's how I started to get at that idea. But this is just the first or second biology course these students have taken. They have a lot more biology in their future if they're going to graduate with a biology degree. And that is daunting because no matter how good your intro course is, it's not necessarily going to help students survive the weed out of subsequent courses. So this is very much a start. I'd like to think that this broad structure of shifting gateway courses to an active learning format, this kind of broad structure could be applied to lots of other courses. Large courses are not going away. We have to work within the first we have to work within the limitations of our system, and then we have to show results and change the system from within if we can, because our results indicate unequivocally, I hope, that the system should change. And that's a very rosy way to look at it, but there's no other way to start making change to these systems that are pretty rigid, but to exploit the openings. And so I'd like to see if this structure could exist in other courses as well within the biology department, and even perhaps within other fields as well. So that students are not just experiencing one evidence-based course, but have at least two for the graduate, yeah.
Looking at the time, I want to just make sure we formally thank wonderful, thought-provoking presentation.
Thank you.
I believe that I'm looking around for Candy and Donna, who are.
I'm here.
Donna, excuse me.
I was getting,
Yeah.
I think they're upstairs.
There is some food upstairs, I believe, right?
They were in the process of